How's everyone doing?
How's that a normal view for you?
I like the cat. That's all. That's you know, no lines, is perfectly fine. It's like a checkerboard.
I emailed you my homework.
Yeah. What?
I emailed you.
Yeah, I just saw it. Let's see what's going on here.
What's the next for the page? How are you?
I'm ready for the semester view.
Yeah,
Same. How do you guys want to do finals?
I'm down for.
A pluses?
Interesting. Interesting. Okay, that's negotiable. We actually can't give A pluses. So I can give you an A and a handshake or a star.
Why can't you give A pluses?
There are no A pluses in the CSU system. Don't leave that so bad.
You get full credits for it, right? You're not-
A is four.
Yeah, you're not getting any more than what you, yeah. That's more than.
I go and I go to try and click A plus, you know, because like, you know, Rolando needs an A plus and it just said.
Yeah, it does.
Yeah. Well, no, there's H plus.
So, okay, so. Okay with appointments or do you want to find?
I'm okay with appointments.
I'm okay.
I'm okay with appointments, but again, I gotta get working extra double time, so get backtracking some of the.
Yeah. We wanna make sure that it's comprehensive in the work that we do.
Yeah.
So I will ask questions about the earlier parts of the homework and I may or may not have a problem. That you do. Maybe, depending on how stressed I want you to feel. You have a preference for finals or check-in? Okay, so check-in. Okay. Okay, and then this is the most important part.
So these,
Yeah,
oh yeah, what's that then?
I think I've done yours already.
I know that 2 people have.
Oh,
Well, that's
really?
like almost such class.
That's 50% of the class that's currently here, but it's
Oh,
not 50% of the class.
there's more people in the class?
There's 2 more people in the class. Sarah's online and Yasmina's possibly gonna watch this afterwards.
Okay.
So I'm only talking to you 4 right now, because if I can get that to 4 out of 6, oh, that's a great success rate. In my PHYS 3300 class, which has 11 people, guess how many respondents I had?
2.
11?
0.
Oh, shoot.
So I'm gonna yell at them today. Interestingly enough, and you know, I don't think this is necessarily always a fair way to do it. You know, I care about the studies because I want to make the next version of the class better. But faculty member, generally, they look at like how well you did in your studies. And then they assess whether you're a good teacher. I'm like, all right, 2 people respond to a class of 6. That's not really representative, but that's fine. So if you want to impact how this class is taught in the future, and also my own teaching in the future. Comments, questions, concerns? Okay, what were we doing? Does anyone remember?
Complex integrals.
And
Yeah.
what complex interval were we doing?
Cauchy-Riemann relation term or?
We're gonna talk about that today.
Oh, no.
But we were looking at something like this perhaps. It's a really good XY space in there. So here's X, here's IY. And we start over here at some distance R. We went around in a perfect circle,
Okay.
right?
already
And what did we
watched.
find out about that?
Uh,
C1 is equal to the integral of C1.
oh,
Like 2 pi.
2 pi what? 2 pi I.
that's about it.
Good. And then we went from here, but this time we only went to this point. We found that it was C2
I,
pi I, correct? So half of that. Good. And then I had you do something crazy, and I said, let's go straight up in a line to this point, and then straight back down to this point. And I called this C3, 1, and this one was C3, 2. And we sort of set it up. You know, I showed you what the path would need to be. What was the path supposed to be?
I have a,
Not necessarily reading off, what was the form of the path?
well, it's linear.
Take a line. That's all I need, right? So it was a line up and a line down, and then we just integrate along those. Right? Okay, and you did that integral when you got home, because
Yes.
you're good students. And what'd you find out?
It's also pi I,
What the fuck?
so something's wrong.
So
with
something's
complex
crazy,
pi.
right? So here we said C3, and just as I predicted, because I already knew the answer, it's also pi I. So remember that the motivation for this section was trying to understand, what does it mean to do an integral in a complex space? Because we thought originally about integrals as being the area under the curve, and yet that is kind of indefinable here. Because there's not an area underneath the curve. I asked you before you did the integral, I said C2 should be larger than C3, based on if you just look down to the X, area underneath the X, right? That's clearly not the case though, because we're not representing the area under the curve. So in fact, the integral here is a contour integral or a path integral. Because what we are not seeing here on the screen or on the whiteboard is the fact that the function f of z has a shape. And I'm trying to evoke this imagery in your mind. Maybe it's not working, maybe it is helpful, you can tell me afterwards. But it's not simply walking from here to here and then here to there, or going around this curve. But it's imagining, if you imagine you're in a 2D space, that f of z is the topography. And so as I walk along this path and this path, it's the same distance, where the distance would be the integral, as this C2 path. Now, distance is not the right way to say this, but this is the imagery I'm trying to evoke. Does that make sense? Yes or no? Do we want to finish the integral, or are you guys good? Did you do it? You did?
No.
You did?
I did do it.
Right.
I got it.
Right. A's, B's. Just kidding. No, I'm good. Okay, so okay, it's not horrible. I'll write just what it should look like and I'll let you go from there. So hopefully you got to this part. So we recall that the function that we were looking at, f of z, was 1 over z. You recall that? Okay, so then the integral C3 of basically dz over z for the line elements that I picked is the sum of 2 integrals. And so I'm just gonna write this down. You're welcome to do this on your own afterwards. So it'll be of this form, where r, of course, is the radius of that circle. Okay, so the first one says the integral from 0 to 1 of dt, where the top is the real part is minus r plus ir, all over r plus t, and that's multiplied by minus r plus ir. Okay, and then the second one is the integral from 0 to 1 as well, because we just broke this up from time going from 0 to 1 and then from 0 to 1. We split the timeline independently in those 2 coordinate systems. And then this one is minus r minus ir all over ir plus S, but you might call this one like T1, I think maybe was what we originally called it, T1. And let's call this one T2, just to clarify. Minus R minus D T2. Yeah. That reasonable? Okay. So, yeah, you can pop that into Wolfram if you want, or you can figure it out. I think one of them was like a inverse tangent function, and the other one is a logarithm, and basically they come out to pi. Right, and that's the shocking result. Okay. So even though the paths are different, the integral is the same. And that wasn't necessarily expected, but we'll see that in certain circumstances, this is the case. And we can use this in order to understand more about our functions in the complex space. Okay. If you you close this path from here to here to here to here, and then I went backwards through. What would the integral be? Maybe that's not obvious.
Right, or no? In 2 pi, it would be the same as a circle.
Is it the same as the circle though? No, because I go through the origin now.
Oh.
Okay, this is maybe throwing too much into this.
No.
Let's work out some interesting things first. Okay, we're gonna have some motivation here. What?
I thought it was gonna be 0. Can you go back to the word?
So remember, we went back to R here,
Yeah.
and we got a real number. Well, not real. We got an actual number. We didn't get 0. We got 2. So going back to where we started does not get you back to 0.
Okay.
That's really important to remember, because this is
Oh.
not an integral of the area under the curve. It's did I go anywhere? Essentially, right? It's a weird way of saying it. Did I go anywhere?
Okay.
Right? Sometimes you don't go anywhere even though you've moved.
Okay, I get you.
Okay, right, all right. So now let's ask one more question, right? So, or maybe not a question. Let's write Couch's theorem down. So I'm gonna make a couple of statements. So we said that f of z is analytic. We said f prime is continuous. Okay. And it's continuous at each point within and on the closed contour C. Okay. This one's gonna bother you. Here's Couch's theorem. That's a pain. How cheap there. All right. You seen the symbol before?
Yeah.
So
Yeah.
line.
Close. Okay, around some contour C. What? I don't like that.
I didn't see one wasn't 0.
I did say C1 was. C1 isn't. T1 is 2 pi I. I know, we're gonna get there. So, we have a couple things here, right? We said that f of z is analytic. And we said that f of z prime is continuous at all points along C. We're gonna see, hold on. Let's not get ahead of ourselves. Let's first prove this and see if it's true. And then if it's true, right, if Cauchy is not lying to us, this will tell us something about holes which may exist within the contour. Okay? So you're absolutely right to be very skeptical. This is the right instinct, right? This is telling me, one, that you're paying attention in class, and two, that you're not trusting what someone's saying, which is what graduate students do, right? Graduate students always say, oh, this fucking professor's lying.
Oh.
I'm gonna prove this in some paper, and then sometimes you do, and that's how science gets moved forward. Okay, when you're a kid, right, you like believe everything everyone says, and then you get older and you realize everyone's stupid except for you. What?
Who's
Who's Cauchy guy? This 200 years old, that's been old man. Okay, so first we'll need something called Green's theorem. Have you heard of Green's theorem before?
Oh, yeah, yeah.
Oh, you're
I know
familiar.
that.
Okay, so I'm not going to prove it then, because I didn't want to anyway. So we're gonna trust that Green, cool guy, I guess, whatever.
Yeah.
No actual idea if he was a fucked up person or not, but nice theory. And we're gonna use this to investigate whether Cauchy's theorem is a bunch of bullshit. Okay. So we need something that will take the integral, contour integral, and turn it into
A double.
yeah, right, that would be Green's theorem. Okay, so let's try that first. So first, let's write f of z. Let's assume instead of using the u and v that we've described before,
Oh.
let's imagine that we have two components. We're gonna call P and Q. Let's call P and Q two functions with continuous derivatives. P, Q are functions whose first derivatives are continuous within the closed on C. Okay, that's really important here. So we're gonna write this, oops. We're gonna write this closed integral C of this two pieces here, P dx minus Q, oh sorry, P dy minus Q dx. Okay. Well, we're gonna break this apart into a double derivative using Green's theorem. And you'll see why I chose this weird thing. It'll be really obvious in about 10 seconds. Okay, so this is a double derivative over some region R. Right? And typically Green's theorem allows us to convert something of this form to something with some derivatives. So we'll look at dp dx plus dq dy. And that's all evaluated at dx and dy. Right? Okay, so that makes a little bit more sense why I needed to define something that had continuous derivatives along C, no? Sorry, hold on. Okay. So let's do the first part here. Let's write f of z in its typical form. So f of z is written as u plus I v, and dz we're gonna write as
GU.
Yeah.
X
And then
plus I D Y.
What?
dx plus I D Y?
Yeah. Remember that the line element in the z space is dx plus I dy. So little step in x, little step in y. Okay. Okay. So, let's put this into this, this integral I. Which we're gonna write as integral of u dx minus v dy. That would be the first part. Plus I, the integral of v dx plus u dy. Right? Is that fair? Because we just multiply. We have this piece here, u plus.
Because z equals 0, right? Because z equals 0.
Hold on. Let's not get ahead of ourselves. We're gonna add a couple letters. We're gonna see how these things compare to one another. So here I showed you how we can take this contour integral and turn it into a double integral. And then we have our integral here, which you're just writing in a form that we've already seen before. We've done this before. I'm just rewriting it up there. Okay? Okay, so now let's apply this. Do you see this? How that looks like that?
Yes, I see it.
This one minus this one? This one minus this one?
Okay.
Looks like this one. Correct or not correct? This minus this. This minus this. Right?
I just don't see how it connects to like the Green's theorem one.
Well, we need to turn it into this,
Oh,
right? So using this formula that we just wrote out, now I can rewrite these double contour integrals in terms of two. Yeah. Right? Okay, so here's the first one. Del of minus u del y plus del of minus v del x all multiplied by dx dy plus I double integral again of del minus v del y plus del u del x dx y. Well, that's silly, right? Why is that silly?
Um, V partial Y supposed to be equal to each other, right?
What do you mean by that?
The partial V, partial Y.
Partial v what? Can't just say partial v, right? It's partial with respect to something.
Yeah, partial V with respect to Y is equal to partial U with respect to X.
Interesting. So you're saying that this is 0? When I add them together?
if it's.
Yeah, if it's continuous, right, which is our requirement here.
Yeah, they're continuous, yeah, because they're equal,
Continuous and analytic.
yeah.
So you're saying this integral here is 0? Even before you integrate it?
yeah.
Huh, that's funny. What about the next one? Why? Oh, interesting use of the Cauchy name, right? Okay, so this is a natural extension of the Cauchy-Riemann hypothesis, right? So Cauchy's theorem here shows that it's identically zero for both of them. So that proves Cauchy's theorem. Okay. Questions? Feel uncomfortable about that?
Okay, okay.
You feel uncomfortable about that, Rolanda?
I'm okay with it.
Okay. So, let's try one thing, let's draw it out, because we love drawings. Imagine 2 points.
Imagining.
Let's imagine this path is C1. This one's a little funnier. That's C2. So I would like for you to demonstrate to me that the integral of v of C1 equal to the integral
F of C, C1.
Yeah, let's assume f of z is some continuous function.
Okay.
That satisfies the Cauchy-Riemann relations.
I mean, you didn't really give us any functions for C1 and C2, right?
That's correct.
You don't-
You don't need them? Okay.
Interesting, interesting. Huh. Huh.
But I don't know, like, prove.
For this piece,
Oh, no, sorry,
For this.
contour, yeah.
this is
contour.
I'm asking, is this true?
Well, and this is what I'm saying, cause I'm writing now basically the same thing for FMC, DZ, FMC, you know, and the only thing I'm writing differently is the C1, C2.
Yes, that's correct. Do you need math to do this? No, why not read?
Yeah.
But it,
Oh.
It's not an
Not
enclosed loop.
closed loop, it's not a closed loop.
well,
C1.
so if you go from A to B and then backwards, that's where you get the negatives,
Yeah,
right? So if this is true, then they must be equal and opposite, right, on the whole path. So if I go from A to B, then when I return along minus C2,
That'll be equal to 0.
it has to be
Yeah.
according to calculus,
Okay, okay.
right? So I don't have to calculate.
yeah, you know.
So this is really powerful, right?
So you were missing.
Oh,
No, but you minus it from both sides, then it's equal to 0.
It's more like-
Let's move the other way.
Remember that if I go from one end of my integral, if I go from A to B versus if I go from B to A, I always get a sine flip,
Yeah,
right? So we can use this for figuring out more complicated integrals, right? So let's imagine, and I'm not gonna go back to our example that we had before, because you didn't know that, right? Let's say you have several paths to choose from. Okay? You see an easy path to calculate, and you see a much more complicated path to calculate. But you need to know the more complicated one. If you can use those two paths together to complete the loop, then you already know how to calculate the more complicated without actually calculating.
Hmm,
Does that make sense?
yes. Path of least resistance.
Yeah, more or less. Let's try another one. This one's gonna be fun. And not fun, but you know. So these ones, the two that I'm thinking of right now, you're gonna be low on like the math and more on vibes, okay? Let's imagine two closed contours. Change this so that it's not. Let's imagine a contour like this, big old potato. Let's go that way. And let's do a contour like this. Let's call the contour C. Let's call that contour gamma. Okay. So what is the relationship? Of C, of Z, dz. To gamma. Of Z. You're right that they're.
Yeah. that's
So
what
you're
it-
saying they're both zero.
They're both closed,
yeah, but wasn't it, what was it, like, what was it? Like,
yeah, cause they're both starting and ending at the same point, I'm assuming.
So
Well, they're
hold on,
different
hold on,
points, but.
hold on, let me say this different. Say this different. If it's analytic here.
But not in gamma?
But not necessarily anything.
Oh.
then it wouldn't work, because catches their moment, it's having these, analytic.
So one's zero.
Even though everyone on the contours analytic.
So we're gonna do some funny. We're gonna do funny business. Okay, so here's the most fun that we have about contour integrals, is that. You know, contour C, for example, and you'll see where we're headed here in a few seconds. Contour C may enclose a non-analytic part of space. Okay. So we're fucked, right? There's nothing we could possibly learn about it, right?
Okay.
Is that true?
I
No. That would suck, bad class. Okay, so now let's imagine, let's do something really fun. Let's build a tunnel. Right?
Yeah.
Yeah, awesome. Okay, so let's build a tunnel. And that's the new contour.
Oh. Well, now everything enclosed, Emily.
Now everything enclosed is analytic, correct? So what does that mean about the relationship between f of z around C and f of z around gamma? What?
Why did that make everything close and?
Okay,
Cause now the singularity or whatever is on is on outside of the,
yeah, let's say, I mean, this doesn't have to be, let's imagine that, I mean, the one that you said first, right? If everything's analytic inside, then obviously it's trivial because they're both zero. So they obviously equal each other. But if there is a piece that's not analytic in here, then if we can cut through this space and we provide two new cuts, so this one goes like this in that direction, this one goes like this, so this would be C1 and C2, two little cuts. And remember, this is all mathematical, right? So we are gonna be able to say stuff like, you know, in the limit that the cuts get really small or they're very close to one another. So I've widened how big this gap is for our edification so that we can see it, right? But mathematically, we make them almost touching, right? Okay. So what is the contribution then from all four of these pieces to the integral?
zero.
Well, I mean, the whole thing's gotta be zero.
Yeah.
Because the interior between the two of them was analytic everywhere, and therefore, according to Cauchy's integral, it must be zero. So let's look at each piece now. Right? I have this contour integral plus this contour integral plus this path integral plus this path. What do these path integrals do?
Probably can.
They cancel out.
Half it, right? And so therefore, these two are,
They're gonna have to be equal, yeah.
yeah, well, I mean, the path,
Well, they're
The paths are backwards,
opposite,
right?
opposite, yeah.
well, they are equal because their original paths are opposite. When I
Oh.
connect them, their paths connect smoothly, you see?
So they equal the negative of each other or no?
No, they're
Yeah.
just equal to each other.
If they were, if
As
they
long
were
as-
flipped, you'd have to.
Yeah, as long as this one is flipped from the inside, right? So when I originally drew C, it's going
Counter.
counterclockwise, and the interior one is going clockwise. But once I connect them, then the whole system is going counterclockwise. Okay. Cool. Isn't that a fun proof?
Oh, yeah.
All mathematicians, every mathematician online is gonna hate that. It's not really a proof, but it's vibes, right? Okay. So the use of Cauchy's theorem is really important when we talk about Cauchy's integral theorem, which is what we're going to discuss now. And in the discussion of something called residues, which is not what you find, you know, like the gunk underneath your chair or whatever. These residues are mathematical, and they're gonna have really important meanings when we want to integrate over singularities. Questions about this before we move forward? Okay. So here is Cauchy's integral theorem. Delete all this. So Cauchy's integral theorem says that as long as you have a function that is analytic within and on a closed contour C. So f of z is analytic on and within C. And C, Z0 is a point within C. Then I can write the function evaluated at Z naught is 1/2 pi I. The integral, closed integral C of f of Z over Z minus Z naught dz. Why is that not trivial? Why is that not identically zero? What have I done different than that Cauchy's? What's that?
So I'm reading it from text
Okay.
and read it out loud.
Yeah, it's okay, it's okay.
So if you have a poll in your.
Ah.
Yeah,
I added a pole.
yeah,
So before Cauchy's theorem said that the integral of f of z around some closed contour is identically zero, except for potentially in times that we're about to see something else different, blah, blah, blah. Right? Here, what I did is I introduced a pole. What's the order of the pole? First order, good. All right. And here it says something like the value of f of z there. Huh. Is this hogwash?
I don't know how it means.
right on.
Great honesty. I do love that honesty.
Great.
Okay, so let's think about how would this be useful? Okay. It's- So basically what this is saying is that the value of an analytic function anywhere inside the closed contour is uniquely determined by the values on the contour itself. Okay, so the choice of the contour matters a lot. Okay. Should we, you guys want to prove it, or do you want to just use it?
I'm good.
Yeah,
We're prove it? Sure.
that's.
So let's use this one. Start with 24.3. Which is that one over there. Good thing I left it up. I said those two are equal to one another, right? Okay, let's really look at that geometry really quickly. Let's take gamma. Now we can change the shape and the size of it, right? Because we're allowed to do that.
Oh.
Mathematics about it. And let's center it. Okay, so I'm allowed to change this. Everyone's okay with that?
Yeah.
I'm allowed to change it. And now let's find some point Z naught. Okay. And now I'm gonna make my cut here and here. Build this contour. Now I'm gonna make it just like that. This is gamma. Here's C1, C2. Side's going around like that. So it's gotta go up, this is gotta go down. Gotta go counterclockwise. Okay. Still true?
So Z naught is a point within C.
Mhm.
Okay. Even
Okay,
though.
well, now it's now not within gamma.
You wrote.
Well, originally it was part of gamma. Right, if I cut this. Then it's part of gamma and C.
Okay, yes,
So gamma's now like a little line.
Gamma's just like a little infinitesimal bubble that I put around the Z naught.
Okay,
And Z naught is some location in C.
I get you, but now that's what I'm saying, if you draw the line, now it's technically outside of C. So
Right, right, in order to
C.
prove that, so now if I write it this way, right, so now that it's drawn like this. Now. This is inside of C and inside of Gamma,
Okay, okay,
because I made the lines come close enough together, they disappear,
okay.
and this is true. Right? Like, how the hell are you gonna do this? Okay. So since f of z is analytic inside of C. The integral f of z over z minus z naught is analytic in the space between C and N. So in this space here, the function f of z over z minus z naught is analytic. Why is that?
Within like the line.
Yeah. It doesn't enclose the singularity. Right? We designed it not to enclose the singularity. So the top is analytic, the bottom is analytic, so we're happy, right?
Yeah.
Okay. Then let's use the fact that any point C on gamma is given by this. Z is equal to Z naught plus, this will be the modulus rho exponential I theta. Right? And similarly, we could write BZ as I rho exponential I theta d theta. Is that right? Okay. So let's now evaluate the integral. Okay, so let's write I. And we're going to do just this little one. Okay, so here's the integral of gamma closed concord f of z over z minus z naught. Okay. Oops, we just have to do z naught. And I'm going to use these definitions that I just wrote. And I'm going to say that we're going to go around this circle. Made it a circle, because obviously. Let's do f of z naught plus rho exponential I theta. That's that's the argument of f all over this rho exponential theta. Now this is going to be multiplied by our dz pieces here. You see the dz pieces? Oh. Very careful, right? Oh, very fun. Okay, so this is I rho exponential theta d theta. That's convenient, right?
Oh, why? I like that.
This piece and this piece, they cancel out, I comes outside.
Wow.
So this piece is just I, the integral from 0 to 2 pi of f of z naught plus rho exponential I theta. The I was outside already. Okay, so let's just have a quick look at that. So what happens as rho goes to 0? Excuse me? You just have Z naught. And what did I claim?
Z naught.
Oh shit, it's all that stuff, bro.
Okay, okay.
Isn't that a weird way to prove something?
No, I
Just
mean,
do it and then, oh yeah, it kind of works. Okay. So do you see this? Right? So as rho goes to 0, this term disappears. The loop gives you 2 pi. It's not dependent on I theta. And then you just divide. Great, right?
Road,
Rho is like
just making it up, or was it something?
this is all made up, right? So what was I saying here? So z was just like some distance here to z.
Yeah.
But I want to go around the circle. So I'm going to start at z plus
and that's a
some
circle.
little enclosed radius circle, rho exponential height. Is that okay?
That's okay.
And remember, I'm allowed to do that. Right, because like, just like you would say, like, along the x number line, we'd have some length 4 plus minus 2. I can just build a little circle in the complex plane because it doesn't see the difference between x and y. As long as I use this argument I theta, then I can circle around in xy space.
Okay.
Cool. Okay, that was kind of fun. Right? You can also show, I don't think I'm gonna do it here. But you can show that the nth derivative of f of z, so let's do f, and this will just be some number of derivatives of z naught is going to be n factorial on the top all over 2 pi I, the integral over some closed contour c of f of z dz all over z minus z naught. Just want to be careful here. N plus 1.
Now this function z naught is raised to the nth power?
No,
Or-
this is saying the nth derivative.
The nth, okay, the nth, okay.
Right, so we could say for the first derivative, right? So, this one is the one that you just saw, and so you would say 0.
Okay,
The 0th derivative would be the original function. And so you can see that this is still true, right? When n equals 0 in that formula, you get a 1 on the top. 0 factorial is 1, and on the bottom, you have a polar order 1, because it's n plus 1. So what does the first derivative look like? Well, you still get a 1 here, because 1 factorial is still 1. But this would be,
that would be squared, it'd be,
right, z minus z naught squared, right? Now let's say you want the 12th derivative.
be the 13th power on the bottom.
Very good. That makes sense?
12 factorial.
Yeah. I don't think we'll do that. Okay. Um,
No, that's good.
so this is important because the value of the analytic function, if that's known on C, then not only the value of the function at any interior point can be calculated, but also the values of all of the derivatives because of this relationship. Does that make sense?
Okay, so that's kind of helpful.
Okay, so typically this is the part of the class where you probably are supposed to learn about Taylor and Lorentz series. But I'm just gonna not prove that those exist. Do you guys know what a Lorentz series is? You know what a Taylor series is.
Yes.
Yeah.
Let's just define what a Lorentz series is then, which is the power series representation of any function that we need to use this in order to understand what the residue is and to understand Isabel's yearning question of why the fuck wasn't that first contour equal to 0 for his line. Alright, let's just really briefly talk about the Lorentz series. Lorentz series is just a special Taylor series. Um. Alright. So. Question? We're good?
That was like the other Lawrence.
Oh, Lawrence.
That's the only reason, that's what.
Oh, like the laboratory Lawrence.
No, this is the old school. Okay, so here's the Lorentz series. You have some F of Z. It's going to be equal to a power series representation, which basically has the form a to the minus p. Okay, and I know that's gonna feel very uncomfortable. It's not to the, but the subscript is on the bottom, minus p. Okay. B minus z naught p, p, positive down here, because it's on the bottom. Okay. Dot. A minus one, so this will be z minus z naught, like that. Okay, the next one is straightforward, that's just a naught plus a one and z minus z naught plus a two z minus z naught and so on and so forth up to infinity. Okay, as long as a minus p is not equal to 0. Okay,
It starts negative and gets bigger.
so Taylor series you're familiar with, right? Starts there.
Yeah, it's just, okay. But so this one can start at a negative. Degree,
Yeah, it can start, and it needs to start at a negative degree for it to be useful to us.
okay.
So we're gonna utilize this fact because we've already learned about something that looks a lot like that. Right?
It's very true,
Okay, so we're gonna use that math part. So the coefficients can be found. And in fact, we're gonna show that the should I get that one right? Yes. So how do you find the individual coefficients? Well, for a Lorentz series, you will have something like A of n is equal to 1/2 pi I.
The big one.
What? I'm conscious about my one. Okay. Let's do a 2 pi I. Integral, closed integral. F of z. All over. Z minus. 1. Easy. Cool. That's the definition of the Lorentz series. Okay, so there's just one tiny problem here. If f of z is not analytic at z naught,
Oh, you're saying, well, you can make it.
what do you mean?
You do the integral theorem, and you did the little line, the little cuts.
Well,
Okay.
okay, we're gonna get to that in a few seconds, because that's gonna influence how we think about our integrals. But if f of z has the form, this form here, right? It has a pole of order p at z equals z naught. The value of this one here, a to the minus 1, is called the residue. That's in.
Say that again,
It's just a definition.
it's,
If the function f of z is not analytic at z naught, and it has a pole. Okay. Then we call this a minus one component, just the a minus one, not the whole term. Right, and we say, we write it like this, as it is down here. We say this is called the residue. It has a special term because it shows up over and over and over when we do these complex integrals, so they decided to name it.
it doesn't sound like a positive thing. Like do something.
No.
It sounds like it's probably getting in our way.
No, the residue theorem I think is quite.
Okay.
And in fact, this is one of the beauties of using complex analysis at all. I don't even really like complex,
Oh, you don't?
but use the residue theorem, like, gotcha. Okay, so let's talk about it. We saw from Cauchy's theorem that the integral over a closed contour was 0. We said that had to be true if the integrand is analytic within the contour. So now let's go back to our original issue, right? Was C1 or f of z, which we did that nice contour, was that analytic inside the contour? Let's draw the picture again. F of z equals 1 over z. Here is my, let's say I do that wrong. Well,
Oh, the original.
is C1, the C1 enclose the analytic function? Is f
Yeah.
of z analytic in that region, in C1?
Well, isn't it not analytic at 0?
Sorry, you both spoke at the same.
I think it's the same.
Yeah, not.
Which
not-
that?
Not analytic at 0,
It's not analytic at 0, good. There's what at 0?
singular.
A pole. So if I move this circle over to the right to there, what about then? What would C1 be?
And
Yeah, and
Yeah.
therefore the integral of, right, exactly, right? So this is kind of the power. Now we don't have to do any of the integral.
move it.
Well, hold on. Hold on, we're getting ahead of ourselves, right? We haven't talked yet about how we can actually solve something with a pole, right? So let's look at the residue thing. Okay, so it's natural to ask, how do you take this integral when the integrand is not analytic inside C? So the first thing we're gonna do is we're gonna write that function. I'm so bad at writing up words. Okay, we're gonna write the function f of z as a Lorentz series. And the first thing to write is, here's the series way to write it. So you start at minus m, and then you let m, or sorry, you let n get bigger and bigger. And it'll just be a n z minus z naught expanded around z naught. Okay. That fair? It's just writing the Lorentz series. Okay, so this is where the fun part comes in. So let's imagine now, let's use an integral of f of z around a closed contour that encloses z. Oh, sorry, z naught. Z naught. Okay, and I'm not actually gonna use the real function here. We're thinking in our mind, this is how we're gonna solve the 1 over z, but in practice, this is a generalized form. So let's imagine that this region C encloses exactly 1 pole. Okay, exactly 1 singularity, I should say, but no other singular points. Okay, so using this theorem, the integral has the same value as the integral around a circle gamma, right? So that's gamma around z naught. Isn't that true?
Yeah.
Okay, and should I delete it though? let's just remember that we wrote z equals z naught plus rho exponential I theta, and then we had the dz underneath that.
Yeah.
Okay, so let's now write the integral formalism here. We're gonna say the integral of this little gamma, okay, is going to be f of z dz. Right? We're okay with that? And here we have this Lorentz series. So let's put this in here. Okay? And we'll notice that a n does not depend on z, so that's gonna go ahead and be able to come out. So we're gonna have a sum n to the minus, I'm sorry, n from minus m to infinity of a n times the integral of z minus z naught to the power n dz, right? Good. Okay. So this is cool because now we can rewrite this in terms of our rho and our i's, like we did before. The rho and the argument theta, and we can let rho get real small. Same trick we pulled before. So let's write that. So let's write this in terms of sum from minus m a n integral of I rho to the n plus 1 exponential of I n plus 1 theta theta. Okay. So what are most of those terms?
Almost let's look at that data, because we're only integrating with respect to data. Don't forget, what is rho?
That's the modulus.
Yeah,
Oh, no, not modulus, actually. Well,
Yeah.
Oh, is that the modulus of the really small gamma?
And I centered it over the origin to make us happy. What are the bounds for this? For p theta? Good. Does that help well?
yeah,
Yeah, also like in the. Yeah, because that integration of the exponent, that's just like.
What's the integral of an exponent?
Oh, isn't it just like e to the u over u?
E to the u
no, it's,
over u, yeah.
Yeah.
Well, e to the u alpha, and then the alpha would come out if you were integrating with respect to u, for example.
Oh, thank you.
Right, so everything except for theta comes out, right? So you get that same thing, I rho n plus 1.
Yeah.
Right, so let's look at each one of these terms. So this evaluated for some arbitrary term looks like I rho n plus 1 all over I n plus 1, right? The theta is missing, and it's just exponential I n plus 1 theta evaluated at 2 pi minus the evaluation at 0. Well, that's really fascinating, right? Is it or is it not? Are we fascinated?
Yeah, I think so, because you can see like, that repeated value in the exponent. And then they, because it's like, it's 2 pi I times n plus 1, to like, you might need to like maybe introduce a branching point, if we just want like extra value for that.
But remember that when we evaluate the integral, we have the 2 pi version subtracted by the 0 version. And they are,
Well, I mean, they're gonna be
What?
identical.
they are equal. So what is this integral always equal to? 0. Is that true? What's the exception?
It's not,
Is that what's?
No, there's an exception. Look very carefully.
except for it's not equal to 0.
Yeah, it's the only one that's not equal to 0. Because remember, I said this is a sum, no? And n is changing? What's the exception to the rule?
Oh.
Like if n is -1.
-1. Right? Didn't I say this one was a sneaky one? And this is why it's a sneaky one. So all of these contributions from every single one of the terms disappears except for the contribution from -1. And that's our residue. So now let's have a look at what is it, right? So these are all equal to 0. For n not equal to -1, okay, just to be clear. So what is the? Just imagine I wrote this better. So let's imagine, what is the integral now? For n equal to -1, because that's the one that's non-zero.
Well, you're gonna get a pole on the constant.
You just get the I row? Or you're trying to get the,
I mean,
That'll give you similarity, right?
mm,
Right there, that
look carefully here, Okay,
maybe,
will you integrate the exponential? If, right, put n equals -1 in there,
you get one.
you're 1,
you get e to the 0,
yeah,
which is 1. So you don't pull the n plus 1 down. Right?
okay.
Okay, so what's the integral in there?
And then just I row.
It's 0 to 2 pi. It's I,
Row,
is there a row?
row to 0, oh, it's 1.
Good. What else do you have?
D theta.
D theta. Oh shit, and what is this?
That's it.
What is this thing?
Fine.
It's
Yeah.
I to pi.
Oh, that's funny, that looks similar. Okay. You see where we're going? Oh, sorry, I have that. All right. So therefore, the only term that contributes is the singular pole at the residue. And it contributes 2 pi I a to the -1. Okay? So the integral around any closed contour containing a single pole, generally of order m, it can be whatever order m you want, is equal to 2 pi I times the residue at that location. Yeah. We have some contour. In that region, you have one pole of any order, I don't care. Be as high as you want to be. Okay? That single pole contributes to the integral 2 pi I times the residue evaluated at the location of the pole. So let's go back to our original idea. What was the? Fuck, what do we think the residue is of z 1 over z? No, the residue, remember this thing? A minus 1.
Just 1.
It has to be 1, right? Because we did the integral properly. Shit. So in fact, Cauchy's integral theorem, okay, which is great, we just found out about it, super usable, and helps us to just simply, we find the poles in the complex space, we can do the integral. Because we know the closed contour is 0. And then if we enclose any pole, you gotta add 2 pi I times whatever the residue is.
Okay.
Make sense?
Yeah.
Okay. You'll see how fun and powerful this is on Wednesday. That's actually, we got pretty far. I thought that we wouldn't get quite as far. So I'm happy with it. Any questions, comments, concerns? How did this homework feel for people?
Summer felt pretty fair.
You want it to be harder?
Yeah, I
I
thought
don't
it,
think I did it perfect, but I actually finished it and didn't turn it in late.
That's great. No, and I love both those things. I will post today's homework and it'll be about integrals and more poll stuff.
okay with the quotient theorem.
I do have a question. No, I'll save it for off topic.
Okay. Cool. Anything else? Please do SOTIs.
Oh, okay, you do want them.
Legally, I do want. Thank you.